Welcome. In this video, I will be proving that for a data set consisting of a number of points with x and y values, the slope of the slope and the y-intercept of the line of best fit will have these values. The way to interpret these formulas is n is the number of points in the data set, and the sigma just represents sums with implicit indexes. So this is the sum of all the products of the x and y values for the different points. Sum of the x values, sum of the y values, sum of the x values squared, and then So let's just jump into it. Okay. The way we define the line of best fit is, of course, through minimizing the sum of the squared errors. All right. So let's define this function here. K of a comma b is defined as the sum of a x I plus b minus I y I squared. So this is the value of the line for different values of a and b, and then we subtract the y value, and then we square this and sum over all the points. All right. So for this function, what I want to do is I want to minimize this function. I want to make this function as low as possible. I want to find the two values of a and b, then make this value as small as possible. All right. So what I really want to do is I want to find the gradient and set the gradient to 0, because if the gradient is 0, I'm going to find the extrema. All right. Yeah. So let's just start differentiating, right? Okay. So let's start by differentiating with respect to a. Let's hope nothing goes wrong. All right. So we differentiate this with respect to a. Of course, this is a constant function with the square outside, so we start by differentiating that. So nothing happens to the innards, so to speak. Then we have to differentiate the inner function. B and y are just constants. So what I get here is I get this times xi, since we're differentiating with respect to a. Okay? It's pretty beautiful. We can expand this a little bit. We can multiply this 2 and this x into each of these terms, and then we can split up the sum here, okay? So we're going to get 2a, then the sum of the x times x, which is x squared. And we're going to get 2 times b times x, and then we're going to get minus 2 times sum of yi xi. Beautiful. Wonderful. So let's do the next one. Let's do the b partial derivative. Right? Again, the same thing. We get the sum. We get the same outer function. So that's just that. xi plus b minus yi. But now, the inner function differentiated with respect to b just gives a 1. We're going to just multiply by 1 here for 1, but it doesn't do anything. Okay, so we actually get the same thing where we just don't have this extra xi term here. All right. Again, we get 2a sum of x I plus, all right, so now we have 2b with neither x or y. All right, so we just get 2 times the sum of a bunch of b's, which is just the same as 2 times n times b, so just the number of b's. And then minus 2 sum of yi. Beautiful. Okay. Wonderful. Okay, so to find the extreme for this function, I want to set this vector here, this gradient, I want to set that to 0. All right? So So either of these, I can just put it here. So this is equal to 0, and this is equal to 0. All right? What I can do here is I can actually cancel out all the 2's. And cancel out all the 2's by dividing through this whole thing by 2. Doesn't really make a huge difference, but it's just an extra 2 I don't have to carry around. And I can also start dropping these subscripts. It's implicit. If it says x or it says y, there's an index there. I just don't want to carry that around. Beautiful. All right. So what I wanted to do here is I wanted to solve for A or solve for B. So this is system of equations of order 2. So I have 2 unknowns. And the thing I always do when I have a system of equations with 2 unknowns is I try to remove one of the variables, one of the unknowns. All right. So I can do that in several ways. And what my favorite method is the method of equal coefficients. Right? So I want to make sure that this line here and this line has the same coefficient at A, so I can subtract them and remove the A term. All right? So what do I have to do here? Well, for the first one, if I want these two to have equal coefficients, I have to multiply this whole thing by this thing, by sigma x. I do the same thing with this one, but I multiply by this thing, so sigma x squared. All right? And then I subtract them. Okay? And let's just do it in the order that we have now. Okay, so these cancel. By design, these cancel. What we're left with, okay, so we're left with this thing here. So we have B, and we have x squared. So we have the sum of x squared, because it's x times sum of x times sum of x, then minus n. So, minus n times the sum of x squared. Okay? And then I take this term here, the constant term there, and I get minus this thing, sigma yx, sigma x, and then I subtract this thing. It becomes a plus. We get a plus this times this, which is a sigma y, sigma x squared. And this whole thing is still equal to 0. Wonderful. Okay? I can pull this whole thing to the other side of the equation, and what I end up with is, I end up with b is equal to, I subtract this on both sides of the equation, so what I get is I actually get sigma yx, sigma x minus sigma y, sigma x squared. Then I have to divide by this factor here because I want to get rid of that. Okay? So I get sigma x squared minus n sigma x squared. Hopefully, fingers crossed, that's the same thing. Okay, so we have sigma x squared times sigma y minus sigma xy, sigma x. So what the difference between this thing here and this thing is that both the terms in the numerator and the denominator are flipped. So I have the minus this term and minus this term, but those two minuses just cancel. So what I've got here is actually the same thing as this. So I'm done with B. All right. It's kind of paradoxically, I started with B. Even though A is first. Anyway, the point is, it works. Now, if I want to find A, I have to remove the B's here. Okay, so I'm gonna. If you need to look through this, just pause now because I'm gonna erase this. Okay, beautiful. Okay, so we're going to take these two, and now we're going to make the the b coefficients disappear. Okay, so I'm going to need this section here again, which I reused for the whole equation thing. So we're going to get a sum of x plus nb minus sigma y. Okay. And what I need to do is this time I need to multiply this thing here. I need to multiply by not by sigma x, but I need to multiply it by n, which is actually a nicer calculation because I don't need that sigma thing. Okay, and this one I need to multiply by sigma x. All right, so I get the same coefficients here. And then I subtract them, and I get 0 is equal to, now we get an a here, and what's here? We have n times sigma x squared. The b's cancel, and then we have minus, right, we get it down here, okay. And then we have minus sigma x squared. Oh, you can already see the denominator is actually already appearing here. And then we have minus this thing here, so that's n sigma yx. And then we subtract this, which becomes plus sigma y sigma x. All right? And if you look at this thing here, by the exact same procedure, that's exactly what this gives. So we have minus this over here. So when we move it to the other side of the equation, or we subtract it from both sides, it will switch signs. Then we get this numerator. And this thing here is actually already this in the correct order. Okay? So that's that. Now you actually technically need to make sure that this is actually a minimum, right? So to do that, I'm going to take the second partial derivative here, okay? So pause if you need to go through this again. Again, it's the same argument. I just don't want to do all the minor details again. Okay. So let's do the second derivatives here, okay? So K A should be a of A is equal to, okay, so I take this thing here, take this expression here, and I take the second derivative with respect to A. Here, this is a constant, and this is a constant. All right, and we can remove this also. Does not belong. So this is a constant, so all I get here is I actually just get, and the 0 is not here either. And there's actually supposed to be a 2 here on each of these spots. Okay. So the derivative, the second derivative with respect to A is going to be 2 sigma x squared. All right? The second derivative with respect to B, however, is going to be, okay, we get anything that comes from this term is a constant now, because there's no B involved. Same with this, okay? So when we actually expanded this, we just got 2 times n times B, which just becomes 2 times n. Because the B, the derivative of B is just 1, right? So the B cancels. All right, and now the cross derivative is, okay, well I can take this expression here and take the derivative with respect to B. That is simply 2 times sum of x's. Beautiful. Well, then the formula says that I have to take the Hessian matrix, or the Hesse matrix, which is this on the diagonals and then this on the off diagonals. That's going to be 2 sigma x squared here and then 2 sigma x, 2 sigma x, and then the 2n here. I have to take this matrix and find the determinant of this matrix. All right? And what this gives is, it gives, we have to make this, you could call it the gamma product, but we multiply the diagonals and with opposite signs. So we get 4n sigma x squared, and then we take minus 4 sigma x squared. And the beauty here is that we're actually getting 4 times the denominator here. All right. It turns out that this number here, the is always positive or always negative. There's a proposition I need, but I'm running out of time. This has actually the correct properties to ensure that this is a minimum. And the point here is that when you take, if you take the points squared and sum them up and multiply by n, this is always going to be either higher or lower than the square of the sums. All right, if the points are different. So it's actually a pretty critical assumption here that we at least have one set of points that's different, because else this can actually be a 0 and we get a 0 in the denominator there. But of course you're not going to make you're not going to make a linear regression on a set of data points that have the same exact values. That would be silly. All right. All right. All right. So when we've ensured that this is actually an extremum, well, that's what this says. If this is positive or negative, it's an extremum. And then we know that each of these values, this value and this value, is positive. Each of the entries in this diagonal are positive, and that tells us it's a minimum. Once we know it's a, you know what? I can actually deduce whether it's a minimum, an extremum or not. Okay, because this Hessian matrix actually tells us about the curvature versus the twist. All right. These two terms from the diagonals are the curvature. The product of the curvature, does the product of the curvature win over the twist? Because if you take a curve that's like this, let's say we have a nice little thing here, but if we start twisting the axes, we actually ruin this nice maximum here. So I know that this should be positive to have an extremum, and I know that these two values are positive, so it's a minimum. So we have a positive curvature at this point, which means that we're going up away from the point. So that was a nice little rescue there. So knowing the meaning of the basic terms actually can help you without actually having the document in front of you. Beautiful. So that was it. Wasn't that bad? Now if you want to do an exponential regression or a power regression, you just take the logarithm of b times a to the x, which becomes log b plus x times log a. So you have to take the logarithm of the y value, but not of the x value. Perform this linear regression, you have an exponential regression. And you just have to reverse this logarithm to find the y-intercept and this factor here. If you want to do a power regression, again, it's similar. But now you actually have to take the logarithm of both the x and the y values, but when you reinterpret it, you don't have to take the logarithm of the a. So try it out. That's all the time I have. Hopefully it made sense. You can pause it and look through it. And if you have any questions or comments, leave them below in the comment section.